There we go. It's working.
All right.
Sorry, we just wanted to see if we can put up on the screen the questions and still film at the same time. So my head is a giant screen right now.
Awesome. Well, anyways, we'll jump right into it for the lesson 6 group problems. We'll jump right into number 1. We're talking about the Niemann-Pick disease.
Starting at number 1 and gonna.
We could start with
idea.
5. Okay, well, we'll start with number 1 then. Be lame. So we're talking about the Niemann-Pick disease, and it's not autosomal recessive. So we know that the disease is going to be found only in the recessive genes, so homozygous recessive, and that heterozygous are going to be carriers but not actually affected. So the first thing that we do is we're going to be looking at the Hardy-Weinberg equation, which is p squared plus 2pq plus q squared equals 1. And so the first thing that I always do is I go for q squared. I solve for that first. So to do that, I'd take the diseased ratio, which was 1 out of every 150,000, and so you just divide that. And for q squared, you come up with 0.05 zeros or so. I think a lot of zeros, 6, 7. And then to find q, you just take the square root of that, and you come up with 0.00259. Which is the answer to A. And then to find P, it all has to equal 1, so you take 1 minus 0.00259, and you come up with 0.99741, which is the frequency of the big D allele in the population. For C, we're finding the frequency of the DD genotype, or the big D genotype in this population. And so to do that, you just square your p-value, and when you do that, you come up with 0.9948. And D, the frequency of the heterozygous genotype in the population, is just 2pq. So you do your p-value times your q value and times that all by 2, and you come up with 0.00517.
Very good. All right, so for the fill in the blank section, number 2, we got A was the frequency of the IB allele is Q, and to find the IA and the IB genotype for the heterozygous or codominant genotype, it would be 2pq. For B, we got P squared, but since it's dominant and it's the heterozygous genotypes will be affected as well. It was p squared plus 2pq. C, we just got q squared because the homozygous recessive will be the only ones with those alleles. That's to find out they'll be the only ones with those phenotypes. Sorry, that's how I should say it. D, the R term is in the Hardy-Weinberg equation, best represents the frequency of the MD because it's the third one. So the MR is going to be the P, M will be Q, and the MD can be R. E, we got, since it is dominant, the P is dominant, we got to find the genotypes that have P, or if P is in any of those genotypes, then it's going to have that phenotype. So we got P squared plus 2pq plus 2pr. And then F is the HBS, or sickle cell anemia. G is monomorphic, and H is Demis. I'm saying that right. And
Deems.
Then Deems. That's why I keep them around. And I is the MHC, or the major histocompatibility complex. Histocompatibility complex. Major histocompatibility complex.
Say that 5 times fast.
I would, but already 4 minutes into 5 minutes.
5 minutes into it.
So.
All right. Well, we'll just move right along to number 3. We're talking about the Marfan syndrome, and it is an autosomal dominant disorder. So we know that the only ones who are going to be unaffected are homozygous recessive. So once again, what we're going to do is we're just going to follow the Hardy-Weinberg equation. We're going to do the 1 out of every 6,000 individuals are affected. So we'll do 1 divided by 6,000 to come up with our Q squared value, which is 0.9998. And then we'll use that to find our Q value. So we'll square root that, and we come up with the answer for A, the frequency of the non-disease allele, and that comes out to be 0.9999. Yeah. So then B, we're finding out the frequency of the Marfan syndrome allele in the human population. So to do that, you can just, once again, you do 1 minus Q, and you come up with your p-value of 0.0001, and then you square that and come up with 0.000001. Yeah. And so that is your answer to B. For C, we're finding out the frequency of the heterozygous individuals. So you just do 2 times P times Q, or you can just add P squared plus Q squared up together and subtract that, and do that 1 minus P squared and Q squared, and either way you'll get the same answer of 0.0001999, and that is the answer to C. For D, you find out of a population of 5 million people how many are heterozygotes, or how many we'd expect to have as heterozygotes. So what you do is you take your 2pq value that we got, and you just times that by 5 million, and we came up with 950 individuals.
Very good. Now on to number 4. It looks like there are 190 individuals, which gives a grand total of 380 alleles in the population. So to find the P or the R squared, divided all of the I found out how many R squared alleles there are. So there are 2 for every of the homozygous. So 135 times 2 plus 45, because each one of those will pass an R squared. So that's like a total of 314. So 314 divided by 380 is 0.8263. So you can, to find Q or R cubed, you can either have 1 subtract or 1 minus P, or you can do 66, because there's 22 alleles within the heterozygous recessives, and there's 44 within the homozygous recessives, and then the heterozygous recessives there's 44. So 66 divided by 380, that's 0.1737. So that's A. B, I went through and had to figure out the frequencies for each genotype according to the Hardy-Weinberg equation. So the homozygous dominants were P squared, and so out of 190 pre-search, so the frequency was 0.6828 times 190. Our expected was 130. The observed was 135, and went through that with the heterozygotes with 2 PQ, and then the heterozygous recessives, or homozygous recessives, which was the Q squared. So to find the expected, and then did the observed minus the expected squared, plugged them into the chi squared equation, solved that out, and got a chi squared value of 6.559 kind of rounded a little bit in the expected. I rounded everything up to whole numbers. So it was a little bit different than when, because Troy solved it using the exact integers, but it wasn't enough to change the significance of it. So it was rejected. So it was 6.5 with a freedom factor.
Degrees of freedom.
The degree of freedom of 2 that exceeds what's allowed. So it was rejected, and I was guessing because what was low, the R2, the heterozygous was lower than expected, as were the homozygous recessives, but the homozygous dominant were higher than expected. So I'm guessing that there was an event possibly that took out a certain amount of the R2, R3. No, probably originally took out a portion of the R cubed, or the homozygous recessives, which put less of those alleles into the population, and there's been a shift towards the dominant alleles. Yeah, there we go.
That's cool. So we'll just head right on, and we'll start on number 5. So for A, it says, what is the frequency of the chinchilla and the CB and little c and this little c genotypes in this population? So thankfully we already have our P, Q, R, and S frequencies all there for us. It's provided in the question. And so for A, we got for the chinchilla, or our p-squared value, it's 0.1369. For our CB little c, or our 2RS value, we got 0.075. For our little c, and which is our S squared value, we got 0.0225. For B, in a population of 2,000 dogs, we would expect there to be 150 dogs, because all we did is we just took our 2RS value and we times it by 2,000 and came up with 150 dogs. For C, a population of 5,000 dogs, we would expect them to have 920 dogs that have the white coat with dark eyes phenotype but are heterozygous. So we just had to find anything that had the CD as the first allele, or the dominant allele, and then anything else below that could count. So we came with CD and CB and CD and just the regular C, and came up with 0.115 and 0.069, and times those by the 5,000 and came up with, and added those values together and came up with 920 dogs. For D, among a population of 15,000 dogs, we would expect there to be 3,112 dogs that have the chinchilla and CB, or the little c genotypes. And so we just took those frequencies again, just like we did in the other parts, times them by 15,000, added them together, and got 3,112 dogs.
Peace.
Yeah.